But let's take a look at how a lot of these papers working on contracts are talking about the purpose of blame. Correct blame assignment gets programmers started with the debugging process. After all, the purpose of blame assignment is to assist programmers with debugging. And finally, blame narrows down the search for the error. What we can see from these quotes is that fundamentally blame has a very pragmatic purpose, which is to help programmers find the problem in their programs. The thing is, we don't really have any empirical evidence to suggest that blame actually satisfies this pragmatic purpose in real programs. So with this project, we're proposing an empirical methodology to evaluate whether blame lives up to its pragmatic promise in real contract systems. And at an intuitive level, our approach poses and evaluates the following hypothesis: that blame has a systematic relationship to the location of bugs in programs. And as a brief spoiler, while our approach can be applied to a contract system in any programming language, we used it to evaluate everyone's favorite parenthetical contract system, and we found that in Racket, blame mostly does live up to its promise. But before getting into the details of our approach and how we applied it, I want to step back and build a common vocabulary about contracts and blame. And I'm going to do that with an example. This is a program that's intended to calculate an infinite stream of prime numbers and print some of them out to the user. The program consists of a number of components, like main, prime, sieve, sift, and others, but I'll only focus on these four for simplicity's sake. The arrows between these components indicate import dependencies. So for instance, the primes component uses values from both sieve and sift. Now suppose that one of these components, the sift component, has a bug that we're interested in finding. By bug here, I mean a mistake that the programmer made in the source code of that module, like typing a plus instead of a minus. And this bug manifests as the program printing out a stream of numbers that contains non-prime numbers. One thing we can do in the face of this problem is we can add contracts to our program. And the contracts establish these boundaries between the components and mediate their interactions at runtime. And along a boundary, each component has the opportunity to establish its own contracts. So for instance, the primes component can establish a contract specifying its expectations and guarantees about the values it provides to main, and main can also establish a contract about those same values coming from primes. And these can be completely different contracts. So for those of you that know a bit about contracts theory, I'm not talking about positive and negative positions in contracts here. I'm just saying that multiple components have the opportunity to attach contracts to the same values. Now these contracts can fall along a spectrum of strength. So for instance, the contract on the output of primes could simply say that it must be a stream. Or it could be stronger in the sense of raising more errors by saying that it should be a stream of positive integers. Or it could be stronger still and specify that it must be a stream of primes. And I want to quickly note that contracts in general can be composed of arbitrary predicates, like this prime predicate that might have come from a number theory library. And this allows contracts to be very flexible and expressive. So our contract is now strong enough that when we run our program, we'll get a contract violation that looks something like this. And what the contract violation says is that the contract system found a number 4 in the stream, which is not prime. And we can see on the second to last line that contract violations also come with blame. And blame identifies a particular component as being at fault for this violation. I'm going to annotate blame with this little accusatory pointing finger at primes. So now we know that the bug we're interested in finding is in the sift component. But let's put ourselves in the shoes of a programmer who maybe doesn't know where this bug is. How should they interpret blame in this context? One interpretation is that primes itself has a bug. Another interpretation is that primes sanctions the flow of a bad value from one of its dependencies through itself and then to the contract boundary that was violated. So given these interpretations and what we saw before about the purpose of blame, how can we use blame to help us find the problem in our program? One thing we can do is we can use blame to focus our attention on the contracts around the component that's being blamed. And we can try to strengthen those contracts and see if we can catch the flow of a bad value from one of the dependencies of primes before it gets there, and in doing so, shift the blame to that dependency. If we can't do that, then the problem must be with primes. So these are the contracts around primes that we can think about strengthening. But we don't need to worry about strengthening the contract that's already being violated, because it's already strong enough to detect the problem. So we can try strengthening one of the other ones, say the one between primes and sift. And what we might find is that we get the same contract violation, and the blame stays on the primes component. And that might be because the bad value didn't flow through the boundary we strengthened at all. And that's fine. But if we strengthen the other contract boundary, we'll find that we get a new contract violation, and the blame shifts to the sieve component. So we can repeat this process and attempt to shift the blame again, strengthening a contract around sieve, and shifting the blame to the sieve component. And now the blame is on the component with the bug that we're interested in finding. So the idea here suggested, from those quotes that we saw earlier, is that blame shifting gives us a way to systematically relate blame and bugs in programs. So we can refine our hypothesis to say that blame can be systematically translated into the location of the bug in a program via blame shifting. So we want to evaluate this hypothesis on real programs, each of which have a single known bug. And the basic idea of our approach is to take this process of blame shifting that we just went through and formalize it into an empirical methodology and perform it in a controlled experiment and see if blame shifting always leads us to get to the bug. So in order to do this, we need to explore the space of contracts in the program. And to do that, we developed this idea of a configuration, which configures every component in the program with contracts at a particular strength level. So for example, this is a configuration for the three components prime, sieve, and sift. I'm only focusing on these three components for simplicity's sake again, but in general, we need to configure every component in the program. Another example of a configuration might be like this, which configures sift with slightly weaker contracts. So these configurations can be partially ordered by the strength of their contracts, forming a lattice that looks like this. And then performing the process of blame shifting forms a path through this lattice that we call a blame trail. I'll show you how that works in terms of the example that we went through before. When we started, we were in this bottom right configuration, and the blame was on the primes component. So we strengthened a contract around primes, and the blame stayed on the primes component. So we strengthened primes again, and the blame shifted to the sieve component. And we strengthened sieve, and the blame shifted to the sift component. And in our example, we stopped there, because we knew the bug was in sift, and we said we've gotten where we need to go. But in general, putting ourselves back in the shoes of the programmer who doesn't know where the bug is, we want to continue strengthening the contracts around the blamed component, because we're not sure if blame has taken us everywhere it's going to go. So we can continue strengthening the contracts around the blamed component until we can't anymore. And when we can't strengthen the contracts around the blamed component anymore, we say that the blame trail has ended, and we can evaluate our hypothesis about this trail, which is whether or not the component that's being blamed contains the bug. In this case, it's sift, so it does, so we say that this blame trail satisfies our hypothesis. Now, the big idea of our experiment is to explore as much of this lattice as we can by collecting lots of blame trails by starting at different configurations and following the blame to create these trails and evaluating our hypothesis for each of them. So we can now restate our hypothesis in more precise terms, in terms of these blame trails, by saying that every blame trail ends on a configuration that blames the buggy component. And this is the version of the hypothesis that we evaluate with our experiment. So we applied this experiment to evaluate Racket's contract system, and we did it using 7 programs taken from previous work on evaluating the performance of gradual typing in typed Racket. And we did it using contracts at 3 distinct strength levels, where the weakest contracts were no contracts at all. The median level contracts were contracts that resembled simple type-like properties, like int to int. And then the maximum strength contracts were contracts as close to full functional correctness specifications as we could make them using Racket's contract combinator system. Now, these programs did not originally come with single known bugs. So inspired by mutation testing, we injected synthetic faults by making small syntactic changes in the source code of these programs to produce variations on the programs called mutants. 228 of these mutants produce changes in the behavior of the program detectable by our contracts, and so we evaluated using these programs. These programs had a range of components, producing lattices ranging in size from 59,000 configurations to over 14 octillion configurations. So it was a pretty big space for us to explore. And through this space, across all the programs, we explored over 43,000 blame trails. And the conclusion from our experiment is that, in the big picture, blame works pretty much exactly as we expect, which is great. We now have empirical evidence that blame shifting works. However, we also found a few cases in 2 distinct buckets where blame shifting did not work in the way that we expected. And each of those suggests specific ways we can think about improving the design of contract systems. In the first bucket, we found 276 cases where blame shifting failed to settle on the bug. And upon analysis, we could attribute all of these cases to the same problem, which was that an expressiveness problem in the contract system of Racket, where the contract system doesn't provide support for writing protocol contracts that were necessary to monitor this program fully. So the lesson we draw from this is that we need to think about designing ways for contract systems to support writing these kinds of contracts. Now, you can read more about these failures in the paper and why we draw this conclusion from them. And you can also read in the paper about how we evaluated a second hypothesis about blame shifting, which tries to capture an intuitive notion about whether, as the blame shifts between the components in the program, it's always moving closer, in some sense, to the bug. And I don't have time to get into the details, but we found 3 cases where this also wasn't true. And in the same way, we found we could attribute all of these cases to a single problem, which was contract violations that were happening while we were checking other contracts. So the lesson we draw from this is that we need to think more about understanding and taming these kinds of contract violations. So now I want to take the last few minutes of my talk to talk about an interesting lesson that we learned that's a bit separate from these failures and the lessons that we draw from them. And that has to do with state and contracts. Because while we knew that state and contracts didn't really play well before performing this experiment, the experiment revealed that state is a much more pervasive problem with contracts than we originally thought. And that this pervasive state in particular can cause blame to shift in subtle ways that we weren't really expecting. And what I mean by that is that before I told you that blame shifts when you've got blame on a component on one side of a boundary, and we strengthen the contract on that boundary, and then the blame shifts to the component on the other side. But in fact, due to this pervasive state, blame can shift in much more interesting and unexpected ways. I'm going to show you how this happens with an example. Suppose we have a program that looks something like this, and the details aren't very important. But suppose it has a bunch of values, and it has this function f that it applies to some of those values, and then it puts them all in a set, and at the end of the program, it walks over the set and prints the values to the user. When we run this program normally, we might see output like we see next to the program here. But now let's think about adding a contract to this program. Say that our contract wants to check that every value provided to f is a member of some set. And suppose that we know that this contract is never going to be violated when we run the program. Adding this innocuous contract shouldn't change the behavior we see of this program at all, right? In fact, we found that it can change the output you see by changing the order of iteration over that set at the end of the program. So let's dig into what's happening here. Our contract checks if a value is a member of a set. And in Racket, sets are implemented using hash tables. So that entails getting the hash code of that value. And getting the hash code of a value means asking for a new hash code from the runtime. And the runtime basically maintains a global counter. And it increments that counter and gives you back the new value as the hash code for that, or the new number as the hash code for that value. Hence, deciding to get the hash code of some value at some point in your program can change the hash codes of all values that get hashed later on. Then, when we iterate over the values in a set, the order of iteration depends on the hash codes of its values. Therefore, when we check set membership in a contract, it changes the order of iteration. Now, you may be thinking, this doesn't really matter, because we shouldn't be depending on things like iteration order anyways. Right? Everybody knows that. And of course, you're right. But I just want to point out that this can change the kinds of blame you see and can cause blame to shift in ways that you probably wouldn't expect. So to see that, suppose that our set, instead of containing flat values, contains functions. And suppose that these functions are going to trigger contract violations when they're applied. And they're going to be different contract violations with different blame. Now when we add our contract to f, completely unrelated to these functions, we're going to change the order of iteration, changing the contract violation we see, and changing the blame we get. So we've shifted the blame just by changing this unrelated contract. And in fact, this is how we found this problem in one of our programs, the KCFA program. So the conclusion that we draw from this, the lesson, is that while we knew that state was a problem with contract systems, it's in fact a much more pervasive problem than we thought. And one thing we can think about in the future design of contract systems is thinking about how we can prevent these kinds of problems. So I just want to conclude by saying that this project was inspired by the theory of correct blame and the semantics of blame, and it has now provided us some evidence that we can use to feed back into our understanding of semantics of blame. And it forms this kind of loop that looks like this. And in the future, I'm hoping to go around this loop again in thinking about some of these problems that this experiment has revealed, and hopefully find more ones. Thank you.
Any questions?
Thanks for the really interesting talk. That's very thought-provoking. Just to clarify, when you're doing the adding the contracts in, is the strengthening,
Yeah.
is the assumption that there's some notion that the strengthenings are correct, causing the pushes, and uh,
By correct, do you mean they're like it's always getting stronger?
that's sort of the question: is what like when you make a change to a contract, what are the assumptions about the change to the contract? When you what does stronger mean?
Yeah, yeah. So basically, we mean stronger just in the broader sense of raising more errors.
Okay.
And we take it as an assumption of our experiments that you have contracts that are ordered in terms of strength. So in our case, we had those three, and they were at none, types, and max. And so we assume that like one basically subsumes the lower one.
Okay. And then there's some notion of stronger but correct with respect to the specification of the program, like that the programmer changes the contract in a yeah, like that. Well, yeah, what Matthias said. But do you have a full spec of the program, and at the interface you're actually making an improvement of you're refining your spec toward the full spec?
So for these programs, we did not have a full specification. We made a best effort to specify them as well as we could, and we ensured that without the bugs, the programs ran without any issues.
Okay, great. Thanks.
Okay. I think it's far more than thought-provoking. Very nice new empirical method. Thank you very much. On your 460-something cases where you have contracts failing on contracts, can you say something about the nature of the 7 benchmarks that you picked? Are they very higher order? Do you have higher order contracts? Do you have dependent contracts? What exactly fails contract on contract?
So So I think if I'm understanding you correctly, there's two questions there, which is like what kinds of features did the benchmarks use, and then what exactly was happening in the cases where we found violations inside contract tracking. So in the first case, we tried to pick programs that represented a variety of features, and they include things like classes, higher order functions, simple first order programs using data structures and so on. And for the latter question, basically what was happening was that these contracts were exploring more of the program. So what was happening is you had contracts at one level that explored some part of the program's state, and it didn't trigger any violations. And then you strengthen the contract, and it starts exploring more of the program space, and then it triggers a violation that was not discovered by the weaker one, but that's unrelated to the contract you just strengthened.
So I have a question about describing how, say, if you reordered functions, then potentially that would change which contract you violated. So did you consider a model where you would keep executing if a violation failed and try to accumulate a set of failures rather than, because it sounds like you were terminating on the first one?
Yes, so the question is, did we consider thinking about executing these programs in a way that we don't just stop the program when we get the first contract violation, and instead we keep going and see what other kinds of violations might happen if we just kept running? And so we didn't do that, although it's an interesting idea, because generally with contract systems we terminate on the first contract violation, and that's the typical way they're used. So that's the first thing we thought to do. But we have thought a little bit about that, and I think it's an interesting idea, but there are some tricky things that you'd have to work out. So I'd be happy to talk about it offline.
We have a Slido question. So what about different blame assignment strategies? For example, as per the design space of higher order casts by Seek et al. In 2009.
So that's a great question, and one of the great things that we think this approach could be used for is understanding how blame behaves in systems that use different blame assignment strategies, and we can understand them from the perspective of how we can compare the pragmatics of different approaches of assigning blame. Thank you.